I should begin by saying you didn't ask enough questions yesterday, but I already said that at the end of yesterday. I should also say that I am not the least bit concerned with getting through all of the material that I wrote for the 4 lectures. I would rather go slowly and have you understand things along the way. This is not like a course I teach at Northeastern where there's a common final exam at the end and I have to make sure I cover the syllabus. I don't have to get anywhere in here. I will try to finish the lectures, but let's try to finish lecture 1. So this was one of the 10 properties that I listed for Milnor fibers. If you have 2 hypersurfaces defined by reduced polynomials, and the hypersurfaces have the same ambient topological type, then the Milnor fibers are homotopy equivalent. You could hope that the Milnor fibers, the homotopy type of the Milnor fiber, was a very sensitive invariant, and that the converse of this would be true. That if you had reduced hypersurfaces and the Milnor fibers are homotopy equivalent, then the 2 hypersurfaces have the same topological type. You could hope that, but you'd be disappointed, because is the converse true? No, not even for isolated critical points. And like my students at Northeastern, I know that you know this already because you did the homework. You did the exercises. If you take f equals y squared minus x to the 5th, and you take g equals y cubed minus x cubed, the Milnor number completely describes the homotopy type. The Milnor numbers completely describe the homotopy type of the Milnor fiber. It's a wedge of spheres given by the Milnor number. Well, you can calculate these Milnor numbers easily. Of course, I calculated exactly 0 of them for you yesterday. So let me at least calculate this one and let you verify that this one, well, maybe I'll do both. So let's look at the Milnor number of f at the origin. It is the dimension as a complex vector space of the ring of convergent power series, and you mod out by the Jacobian ideal, the ideal generated by the partial derivatives of this. So you get a minus 5x to the 4th, 2y. This is an ideal. These 2 stupid constants do not matter. That ideal is the same as this ideal. You are modding out by y. That wipes out all of those y's. This is the same as the dimension as complex vector space of the ring of convergent power series in x modulo x to the 4th. Well, this wipes out all the powers of x greater than or equal to 4. This is the dimension as a complex vector space of the set of things that looks like a constant plus a constant times x plus a constant times x squared plus a constant times x cubed. Quick! What's the dimension? You get to pick these 4 complex numbers. This is 4. All right. This is not the Krull dimension. It's its dimension as a complex vector space. It's very easy examples. Here, the Milnor number of, where did I put? Yeah, okay. You get a minus 3x squared and a 3y squared. These don't matter. I leave it to you as an easier exercise. I have to verify that this is 4. They have the same Milnor number. They are not, those hypersurfaces, those curves, are not, do not describe hypersurfaces with the same embedded topological type. In fact, you can ignore embedded. The hypersurfaces don't have the same topological type at the origin because this one is one irreducible curve that I will draw as a cusp, but it's It's a different cusp. But it's one irreducible curve. Its link would be one circle. This factors completely over the complexes. It describes 3 lines. And its link is 3 circles. So topologically, those hypersurfaces are very different, but they have the same Milnor number, so the Milnor fiber has the same homotopy type. Well, that's too bad. Sure would be nice if the Milnor number controlled things better. Well, shockingly, that Vietnamese French guy that I keep mentioning, Lay and Ramanujan, this is CP, not the incredibly famous one. Kind of famous, but not. In 1976, proved that, okay, Milnor number doesn't guarantee the same Milnor number absolutely does not guarantee the same topological type, but it does if they're in an analytic family. So, so suppose I have F from some small open disk across U, and my U is again in Cn plus 1, and I assume this takes D cross 0 to 0. And then I define a family, an analytic family, a 1-parameter analytic family, by defining this to be f of tz. So f of t is the kind of thing each f of t for each small t value is one of the things we were looking at yesterday. If n is unequal to 2, and the dimension at 0 of the critical locus of f of t is 0, and for all t. Zero and, too many ands, but I'll live with it. And mu at 0 of f of t is independent of t. So you're assuming the Milnor numbers are constant, is independent of t. Then the ambient topological type is independent of t. Really, I mean, it's not so surprising these days in retrospect, but I don't know. John, I assume this was surprising at the time. You see easy examples with the same Milnor number and completely different topological types, and yet if you assume they're all in one family, that can't happen. I mean, it means that being in a family is a very strong condition, which was probably, which of course you know a priori, but it's hard to believe that that's the only other thing you have to know. In my opinion, it's hard to believe that's the only other thing you have to know. John, were you surprised? As people who know this theorem know, this restriction is because the proof of this uses a very strong topology result, the H-cobordism theorem. And for the H-cobordism theorem, you need your manifold that you're considering to be of dimension greater than or equal to 6. That's the real dimension. Complex dimension n equals 3 would be, and higher, would be dimension 6 and higher. So that's fine. When n is 1, that's real dimension 2, and you can use classification of surfaces to get the result. The n equals 2 case is still unknown, unless somebody proved it in the last day or so, which I'm pretty sure somebody in this room would have heard about. Anyway, so the Milnor number. We love the Milnor number. Why do we love the Milnor number? Because you can calculate it algebraically. Right? It has this nice algebraic description, so you have a prayer of calculating it by hand in easy cases, by computer in more complicated cases. It completely describes the homotopy type of the Milnor fiber, and its constancy in a family guarantees the constancy of the ambient topological type. We love those things. What I tried to do with the numbers I called lay numbers, which is where we're headed, is to generalize these properties as much as I could to non-isolated hypersurface singularities. I want some numbers you can calculate by hand in easy examples and by computer and hard examples. I want those numbers to, in some sense, describe the homotopy type of the Milnor fiber. They will not be the Betty numbers. And ideally, I want their constancy in a family to control the topological type. I believe that Bobadilla has left, but I never conjectured that was true, but I hope by some miracle it was true. Bobadilla proved it is not. But they come close to controlling the topology. Close. Those are quotes. Yeah. So it's where we're headed. I want to replace the Milnor number with some other numbers for non-isolated hypersurface singularities. But before I do that, I want to tell you some Morse theory, because a lot of the proofs in Milnor's book use Morse theory, and there's another theorem of that Lay guy, another theorem of Lay's that's kind of crucial to the whole story, and I would like to at least give you a hint as to how it's proved. And if you've never seen Morse theory, it is stunningly beautiful. If you have seen it, well, it's still beautiful. You just probably won't be overwhelmed by its beauty all over again. But so now, this is really lecture 2. Lecture 2. We will start with multivariable calculus. Hopefully everyone will have seen what I'm about to say. Multivariable calculus. I'm going to give myself a function from R2 to R. I want it to be C infinity. So we have left complex analytic land temporarily. I am in the smooth case. I have my favorite function from multivariable calculus. It looks like this. I'm sure we have all seen the second derivative test. Although I don't know, I assume it's called this everywhere. Brazilian people, second derivative test for a function of two variables. Is that what you call it? You haven't seen it yet, so you don't know what the it is. How does it go? It says this. Suppose P is a critical point of F. i.e. I should say, I'm not going to state it exactly how we state it in our multivariable classes, because I'm going to refer to eigenvalues, but This is what it boils down to. I don't know how it's presented here. Consider the Hessian matrix. The matrix of second partial derivatives. At P. What does the second derivative test say? It says that suppose 0 is not an eigenvalue. Well, then there are three cases. The eigenvalues are both positive, where there could be one repeated eigenvalue. They're both positive, they're both negative, or they're of opposite signs. Then if, let me call the eigenvalues lambda 1 and lambda 2. Possibly the same. Then A, if lambda 1 and lambda 2 are both greater than 0, F attains a local maximum value. A minimum value. A local minimum value. At P. And then B, if lambda 1 and lambda 2 are both negative, F attains a local maximum value at P. And C, and now I really don't know if this is familiar terminology. If lambda 1 times lambda 2 is negative, so they have opposite signs, then F has a saddle point. At P. So it tells you that, oh, either you look roughly like this, so this is A, or you look like this is B, or you look like this is C. Everybody knows this, right? Everybody knows the second derivative test. Great. I want to look at this in a particular example before I state things in general. If you've seen Moore's theory before, this is the example everyone does. Take a torus, which is sitting vertically in space. And So call this M. It's a smooth manifold. And we want to look at our function f being the z-coordinate restricted to M. So the height function on this vertical torus. We want to look at what happens at the critical points, which are easy to see. So let me look at f inverse of the interval from minus infinity to minus 1. Okay, I mean that this is at z equals 0. So there's z equals 0. Quick, what is this? This would be the empty set. Thank you. I know, it was so easy, you were afraid that wasn't right. And you want to let the value of f grow. So I just took the height down here and looked at everything below this. Well, that'd be nothing. But then you let the height grow, and you will hit a critical point right there. And what happens as you pass through that critical point? So what is f inverse of minus infinity to, and now I will say, some epsilon, where epsilon is just greater than 0. Well, actually, I've got it pictured right here. You get a disk. So this is this, which has the homotopy type of a single point. Now here's a bizarre way of looking at it. Up to homotopy, what we did in passing through, so between here and here, we hit one critical point. What kind of critical point? Well, look, it's that concave up thing, which I erased because I'm stupid. It's this case. You hit this kind of critical point. You hit a critical point where both eigenvalues are positive. Right? So I want to write, this is lambda 1, lambda 2, both positive. And what happened when we went through there? Well, here's a bizarre way of looking at it. We attached a zero cell up to homotopy. We attached a zero cell to what we had before. Now, what does attaching a zero cell mean? A zero cell is a point. You take its boundary, which is nothing, and you identify that nothing of its boundary with the nothing we had before, and you end up with a point. Right? Understand, this is a stupid use of the word attaching. Nonetheless, that's how you should think of it right now. You took something with no boundary and you glued its non-existent boundary to this non-existent previous set, and that's why you just have something with the homotopy type of a point. I'm phrasing it that way so that I can phrase it analogously as we keep going. What happens after that? You let your height keep growing. In this region, you hit no critical points. So no critical points. And so everything is a cross product. And in here, this is a cross product. If you want, this is it's a effect. Well, it's almost the implicit function theorem. The height function in between here is a proper submersion, and it's a theorem of Ehresmann that proper submersions are locally trivial fibrations, but a locally trivial fibration over a contractible set is a trivial fibration. And so all you see is a cross product here. Well, if you glue on a cross product with this boundary, nothing changes. And so the topology does not change if you do not hit critical points. It is crucial that this map is proper. So the inverse image of a compact set is compact. This is a compact space. When your domain is compact, your map is always proper. But the more general condition is you want the inverse image of a compact set to be compact. No critical points, nothing changes. But then you hit this one. And what happens as you get just a little bigger than this one? So let me call these values. Let's call this let's call this one B, and there'll be one up here. Let's call this one C, and I'll call this one up here D. So this one, of course, was A. What happens is we pass through the critical point at B. First of all, that critical point is a saddle point. It's so passing through B. Lambda 1 times lambda 2 is negative. So exactly 1. That's the same as saying exactly 1 lambda I is less than 0. What happens up to homotopy? Okay, well, right before you got there, you had this. So before you hit the critical point, you had that. I claim that you, up to homotopy, what you did was you attached a 1 cell. That means, i.e., you glue you take a 1 cell and you glue it along its boundary. You glue in along 0, 1. You do this. You put in, yes, that's not going to fit there. Idiot. You do this. You glue in a 1 cell, just like that. Now, that's up to homotopy. You can describe this up to smooth things of the right dimension called handles. It takes more work because up to homotopy, that's the same as gluing in a strip that would look like this. It's the same as gluing in an entire strip, and then you can kind of smooth it here and smooth it here and end up with something that looks like what we think it should look like, more or less. Right? You end up with something that looks like kind of that part of the torus. Sorry. You're supposed to be picturing smoothing this out and smoothing out this other part and then kind of extending it that way. And I was trying to distort it and make it look, but now it just looks like crap. So I'll just, anyway. You're supposed to believe, you're supposed to be able to picture that you end up with this as you smooth this out and stretch this up. Stretch it. And you end up with, well, what I've got drawn here. You end up with this part. Despite my crappy picture, everybody with me? So then what happens? Nothing, no critical points, nothing changes, cross-product structure in here. And then you hit this one. And what happens at C? Oh, you pass through another one, another critical point. That's a saddle point for us, where exactly one of the eigenvalues is negative. And what happens? You glue in another 1 cell. Right, so we had this. So at C, as you pass through C, so you take F inverse, I don't think I wrote this a minute ago for the other one, but you go to C plus some small amount. What will happen? Again, we're at one of these critical points where exactly one of the lambdas is less than 0. And again, you attach a 1 cell. So you started with this, and now you glue in a 1 cell. And then you fatten it to a handle, and then you smooth it, and you end up with oops, not that. Maybe I'll make this circle bigger. But you end up with a torus with the top cut off, because you can now bring these two circles together along there. And you end up with this. And then finally, you pass through D. And then in D, as you pass through D, lambda 1 and lambda 2 are both negative. And what do you attach? Now you attach a 2 cell. Oh, so I should have said here, I want to explicitly write, attach a 1 cell. In here, you attach a 2 cell. I'm writing less each time, but you attach a 2 cell. And that means you take a 2-dimensional ball, right? You take B2, a 2-dimensional ball, and you attach it along its boundary in S1. And you glue that 2 cell right to this, you glue this 2 cell to this circle along its boundary, and you get the whole torus. This is what Morse theory tells you. It doesn't tell you exactly how the attaching goes. It tells you up to homotopy what you attach each time, but it doesn't tell you the map, it doesn't tell you just, well, I haven't told you the dramatic conclusion, but just knowing the dimension of the cell you attached does not tell you exactly how it affected the homology. You could have canceled homology in lower dimensions when you do this attaching. You could have filled in a hole. And it's, but you can tell how the homotopy, so how the homology groups, for instance, change as you pass through critical points. I don't know if you see exactly what's going on, but when we pass through this point at A, lambda 1 and lambda 2 were both positive. There were no negative eigenvalues. So 0 negative eigenvalues, we attached a 0 cell. In B and C, at B and C, we had 1 negative eigenvalue, we attached a 1 cell. At D, we had two negative eigenvalues, and we attached a 2 cell. This is how Morse theory goes. The number of negative eigenvalues with multiplicity tells you the homotopy type of the cell you attach. Are there questions on this? All right, we need this more generally, obviously. M, smooth manifold. F, C infinity. A critical point of F is non-degenerate if and only if, this is the definition, the Hessian matrix if and only if the Hessian matrix of F in some local coordinates at P is invertible, so non-degenerate. At P is invertible. So. And then the number of negative eigenvalues of this matrix is the index of F at P. It is a very good exercise. I recommend it. It's not, I swear it's not hard, but it's a very good exercise to prove that being non-degenerate is independent of the choice of coordinates. It uses, you must assume you're at a critical point, however. And it's not true in general that the Hessian is independent of the coordinates. The Hessian whether the Hessian is non-degenerate at a critical point, that's independent of the coordinates. And so is the index. That being non-degenerate is independent of the coordinates is easy. That the index is independent of the coordinates, not so easy. You have to know, it becomes easy if you know that this number of negative eigenvalues, oh, this is with multiplicity, I'm sorry, with multiplicity. If you know that this number of negative eigenvalues is the index of the bilinear form defined by the Hessian. So it's the largest space on which the bilinear form defined by the matrix is negative definite. Anyway, I'm not going to, but it's a good exercise, seriously. That this is well defined on a manifold because it's independent of coordinates. All right. So what's the point? The point is that if you pass through a non-degenerate critical point, you attach a cell of index given by the index of the function at the critical point. You need a proper function. It's true that non-degenerate critical points must be isolated. So in a neighborhood, it's the only critical point. But you know, the basic theorems of Moore's theory, basic theorems are if, so I'm assuming F is proper now. So either you should assume M is compact, or some other way you know that the inverse image of a compact set is compact. So F is proper. If the interval from A to B contains no critical values, of F, then F inverse of minus infinity to A is, well, actually diffeomorphic too, but I'll say diffeo to F inverse of B, F inverse of the interval from A to B. This is just what I said before. If you pass through no critical points and your proper map, then nothing changes. And really it's because over AB, everything is a cross product. Because you have a proper submersion onto a contractible set. So this is, really I should call this case 0. I mean, this is kind of the pre-Morse theory case. Nothing happens if you have no critical points. But then there's the real, there's only going to be 0 and 1. This is stupid. The main theorem is that if F inverse of AB contains exactly one non-degenerate critical point, non-degenerate critical point of F of index lambda, then up to homotopy. F inverse of the bigger set is obtained from F inverse of the smaller set by attaching a single lambda cell. So this is how kind of differential calculus relates to topology. I mean, it's really nice. Of course, you have to have non-degenerate critical points. Any questions up to here? Yeah.
Boundary and also form.
So it depends exactly on what you mean. For instance, each one of these, if I chop off at this closed interval, and I don't think I've been careful with the half open and half closed intervals, would be manifolds with boundary. And you're growing from there. But you mean if there are boundaries on the sides? Yes, there is no problem here if your manifold, your original manifold, had boundary as long as there are no critical points on the boundary. If you've got a manifold with boundary and no critical points on the boundary, everything's fine. If you have critical, I'm sorry? So with the boundary, that is a very specific case of stratified Morse theory. The boundary is a stratum. I had originally planned to talk about stratified Morse theory, and then I thought about how much I could actually say in four lectures, and I took it out. But the same thing is true if your only critical point, well, the same thing, that's a lie. Ignore what I just said. The same sort of thing is true if there are no critical points on the interior and just you pass through one critical point on the boundary, you get Morse contribution. There's the Morse contribution just from restricting to the boundary, and then there's what's known as the normal Morse data, which does not come from that. It can be problematic. The real case can be problematic because there's no really nice, you can't get a really nice grip on the normal Morse data. In the complex case, it's very nice. But in the real case, there are lots of people in the room who care about the reals. Personally, I hate the real numbers. I wish they didn't exist. No, I'm just kidding. It's a joke. I mean, this is all real. But no, it's a problem if you have critical points on the boundary. But it is important, and I should have said it, that if M was a manifold with boundary and you never had any critical points on the boundary, nothing changes. Yeah, that's important. In fact, I'm going to need that, so I'm glad you asked. Okay. Manifolds with corners. You know, I'm only good with Whitney stratified stuff. And so if you mean something beyond that, like what I know that people who work in the field of manifolds with corners don't mean Whitney stratified things, then I don't know anything about it. Although, having said that, when you pass from the homotopy statement to the handle statement, the whole problem is that you can attach a handle, but when you attach the handle, so you just fatten up, you just take a cross product with a ball in kind of the other direction that creates no homotopy, and then you glue it in. I think that what that gives you then, I think, is what people are happy to call a manifold with corners. And then you have to smooth the corners to be back in smooth manifold land, right? So when you attach, I didn't mean that. When you attach something like this, you have corners. And if you want to be back in the land of smooth manifolds, you have to smooth those somehow. I think people in manifold with corners smooth corners all the time. I don't know. I don't do that stuff. So, all right. But I do know that technically you must do that to go on. It's in lectures on the H-cobordism theorem. I think all the stuff with handles. All right, let me go on. This would be useless, or not useless, next to useless, if there weren't any Morse function. There weren't any functions with just non-degenerate critical points, which do have names, which I just accidentally said. So f, we're still here, is a Morse function. If all of its critical points are non-degenerate. Great. Well, we wouldn't care about that notion much if there weren't many of them. Now, there are statements about there being dense among all the smooth functions, and there are statements about distance squared from a point being Morse functions. But the one I really care about that tells you that there are lots of Morse functions The one I really care, so there are a number of theorems telling you that there are lots of Morse functions. That if you, basically what it boils down to is if you perturb any function a little bit, you'll get a Morse function. Well, if you perturb in a generic way. But right now what I want to say is if U is open, in Rn, then, and now I've got this F. So I'm thinking of this as U. If U is open in Rn, then for almost all linear forms L, F plus L is Morse. The critical points will move. They will move, but they will become non-degenerate. So you should think, you have a critical point, you add, well, here it's almost all, in the complex analytic situation will be for a generic choice of L. That one critical point will split into a bunch of non-degenerate critical points. But they'll just be near the original one. They won't be at the same place. But the point is, you move things a little bit, you get Morse functions. All right. Milner's Morse theory book. Milner writes great books. How many people have heard that J.P. Sayre is a great expositor? I heard that when I was in my early days as a grad student. And then I agreed. And then I started reading Milner. Makes Sayre look like a hack. Just makes Sayre look terrible. Milner's books are so good. If you have never read Characteristic Classes, Singular Points on Complex Hypersurfaces, and Morse Theory, I recommend all three. They're great. You should read the beginning of Morse Theory before Singular Points on Complex Hypersurfaces. Those books are so good. All right. What happens in the complexes? So now I'm going to return. I haven't told you the Morse lemma, which I would like to refer to in the complexes. So this is what happens when I don't look at my notes as I babble, as I talk. The Morse lemma. So I'm still in the reals now. If F has a non-degenerate critical point, of index lambda at P, then near P, in local coordinates, F equals the value of F at P plus, I don't know if I gave my manifold a dimension. Let's call it dimension M. And let's not use Z's since we're not in the complexes. that, yeah, it says that the function looks like the most basic function you could think of that has a critical point. So here, I mean, all the x's are 0 at p. So that, and it's the most basic function you could think of that would have a critical point at p and has index what I specified, right? Because here you can just see the negative eigenvalues. You'll get negative 2s, and then you'll get positive 2s. So the Morse lemma says yes, up to a smooth change of coordinates. That's what happens at a non-degenerate critical point of index lambda. All right, I wanted that. Suppose now, I really shouldn't use f all the time, but I'm kind of hooked on it. Suppose now we return to our U is an open subset of Cn plus 1, and this is complex analytic. You could define complex analytic non-degenerate just in terms of its Hessian matrix. A critical point P is complex non-degenerate if, well, I'll just write so you take its complex analytic partial derivatives with respect to complex variables, and you look at that matrix is invertible. So there's complex non-degenerate. Great. The Morse lemma still works. If so, I'll put complex Morse lemma. I'm putting it in quotes because I don't think it's usually referred to that as that here. I don't know. Near a non-degenerate complex non-degenerate critical point. I haven't mentioned the index. Well, there's good reason for that. Near a complex non-degenerate critical point, P, F equals F of P. Well, plus and minus, they don't matter in the complexes. After an analytic change of coordinates, you can make them all pluses if you want. It looks like this. There is no index. They're all pluses. Well, that's kind of annoying. But here's the exercise one of the exercises I give you in my notes. This really is an exercise. It's just Cauchy-Riemann at first. Exercise. The critical locus of F is the critical locus of the real part of F, is the critical locus of the imaginary part of F. And so you can look at these functions into R and look at where they have critical points. You know, think of U as being part of R2n plus 2, and just take their real critical points. All those sets are equal. And if f of p is not 0, P is in the critical locus of F if and only if P is in the critical locus of the magnitude of F squared. So there's another real function, the magnitude of F squared. It has very bad critical points where F is 0, but assuming the value of F is not 0, then things are fine. That's the first part of the exercise. The second part is actually easy if you use this. This is part A. Part B. If F has a non-degenerate, has a complex non-degenerate critical point, so does the real part, so does the imaginary part, so does the magnitude of F squared, assuming the value of F is not 0. And they all have the same index. Here I need, there I don't need it, here I do need, assuming F of P is not 0. All have non-degenerate critical points. So that would be real. All have non-degenerate critical points. At P. Of index. All right. This is real 2n plus 2 dimensional. What's the index at a non-degenerate, at a complex non-degenerate critical point? Look at this. Think about expanding it in x's and y's. Just look at the real part. If they're all the same, just look at the real part. How many minus signs do you get? I'm sorry? No. Absolutely not. N plus 1. All the imaginary parts. The square of all the imaginary parts. N plus 1. It's a middle index. Right? We are in a real 2n plus 2 dimensional manifold. All the critical points, if you had a complex non-degenerate function, a complex non-degenerate critical point, but then you look at the real part, the imaginary part, or the norm of the function squared, as long as not 0 at the point, all of those functions have real non-degenerate critical points, and they're all of middle index. This is why Morse theory is so nice, in my opinion. Why Morse theory is so nice on complex analytic things, because of this. And it's what makes analogous results in the reals, like there are many people in the room who are interested in real Milnor fibers, and you could hope to prove a result like probably the one I'm not going to get to of Lay's today, for real Milnor fibers. But the fact that you could have Morse critical points, so non-degenerate critical points of different indices, means you're never going to get something as sharp as what you'll get in the complex case. You could say something about the Euler characteristic, but you're not going to get the strong conclusion. Of course, you shouldn't expect it. Being in the complexes is a strong condition. But all right, great. What does this have to do with anything? Well, in my notes, I give you sketches of proofs of why the Milnor fiber of a hypersurface with an isolated singularity has the homotopy type of a finite number of n-spheres through Morse theory. It is not Milnor's proof. Milnor proved things up on the sphere. I prove it in the ball. I give you that one in terms of Morse theory. The idea is actually very easy. And then I prove Lea's attaching. I give a sketch of Lea's attaching result, which is, without the technical detail of needing a neighborhood of the right form, is easy. But for both of those, it would be useful to me to have the relative polar curve. And I need the relative polar curve next time anyway. So I want, even if I don't get to those two results, and if I keep babbling about what I won't get to, I won't get to it. I want to define, before applying all this Morse theory, I want the relative polar curve. And actually, I just picked this up for the year 73. '73, just the other day, just a couple of days ago, Hamlin and Tessier. So F is still this complex analytic thing. It was real for a while, but those nasty real numbers went away. This is complex analytic. And L from Cn plus 1 to C is a non-zero linear form. And really, I'm going to look at L restricted to U, and I'm still going to call it L. If that bothers you, well, fix it. But what is the relative polar curve? It's actually very simple to define. As a set. It's a little tougher to give it more structure. Well, actually, that was a lie. Just ignore me. Define gamma FL to be the critical locus of the pair FL minus the critical locus of F, and then you close it. Define it to be that. I'm not calling it the polar curve yet, but the theorem is Ham, Lay, Tessier, theorem for generic L gamma FL is purely one-dimensional. All of this is, I'm thinking of at the origin. So I'm thinking of a neighborhood of the origin. Define gamma, so near the origin. If you like germs, I'm always looking at things as germs almost always looking at things as germs at a point. Gamma FL is purely one-dimensional. Purely allows for the empty set. It purely means for all components. And if there are no components, that would still be vacuously correct. So it's purely one-dimensional at 0. 2, the dimension at 0 of gamma FL intersected with V of L is less than or equal to 0. So it isn't just that this is purely one-dimensional, but that it intersects the hyperplane in a zero-dimensional set. The less than or equal to 0, I'm allowing for the possibility that this is empty, and by convention, the dimension of the empty set is usually set to be something like negative infinity. This is just a convenient way of saying, being able to write this to include the case where that is empty. And then there is a 3, gamma FL is reduced as a scheme, is reduced at points other than the origin itself. I don't want to emphasize this one much, other than points other than 0. Let me do an example, and maybe I'll come back to this one. These are the two big properties you want to make most arguments work. This one is just extra. When these are true, at least when these first two are true, I superscript by a 1. I was leaving out the 1 because it's supposed to indicate one-dimensional, and before you know it's one-dimensional, you don't really want to write that. This is the relative polar curve of F with respect to L. Now, I could either state the two things I want to do, or I could give you an example, and I'm prone to examples. So, and as I said, I'm not worried about where I get in these lectures. So, an example would be nice. Example. Let's let F be y squared minus x cubed minus tx squared. This is the only non-isolated singularity I ever draw. I swear, it is. It's the one I drew for you yesterday. It's a bunch of nodes degenerating to a cusp. You would think, after all these years of drawing nothing but this, I would be better at it. You'd be wrong. All right. Okay. So, let's calculate the relative polar curve. I'm going to take t. I'm going to let my L that I was using before be t, and see if that's generic enough. So gamma FL, so that's gamma FT. You take the critical locus of the pair FT. If you think about it, that just means you take the partial derivatives with respect to the other variables, not the t. So you take the partial derivative of f with respect to x, partial derivative of f with respect to y. You require those to vanish. This is the critical locus of the pair ft. You pull out the entire critical locus of f, which will just be the part where t is, where the partial derivative with respect to t vanishes, but just so it won't look so mysterious if you're actually writing stuff down. I'll go ahead and write all three of them, and then you close it. All right, what is this? This is via the partial with respect to x, minus 3x squared. Tell me when I screwed this up. 2x, 2y. And then I'm going to subtract the part that's in the critical locus of f, and then I'm going to close it. Let me do a side calculation that won't be equal to what I get when I subtract, and then I'll erase the part I don't want. This is the same as v of xy, right? The 2 doesn't matter. I can factor out an x. There's v of xy. And then there's union v of still y is 0. And then there's, get rid of the minus signs because they're annoying, 3x plus 2ty. So this, maybe I won't write equals. How about this? All right, the critical locus of ft is this. But the critical locus of f is this part. Right? Because you throw in the partial derivative with respect to t, that would require x to be 0. Once x is 0, you need y to be 0. So, yeah. This is the critical locus of f. And so this is the part we throw away. And so the relative polar curve is this set. Now, you can see that it's defined as an analytic set. And yes, you can do all of this scheme theoretically, but let's not. This is the relative polar curve. And it is intersected properly by where, I'm sorry? Did somebody say something? Oh. If you intersect with v of t, you just get the origin, right? So this is one-dimensional, and it's true that gamma 1 of ft intersected with v of t is exactly the origin. So we certainly have these two properties. I'm not going to bother with this one. That's the relative polar curve. In my picture, it is here. And in fact, that picture is over the reals. And it should be over the reals. It's completely... So if you think of t as giving you a parameter in a family, we are looking at the union of the critical points of all of the individual f of t's that aren't critical points of the big thing. That's what we're doing. And over the reals, well, this part is enclosed by this loop where things are 0. Well, I'm sorry. That's a compact set. And f of t has to attain a maximum and a minimum value on there. And one of those has to occur inside, and it has to be a critical point. There has to be a critical point in that closed loop. Over the reals, of course, that makes no sense over the complexes, nonetheless. All right. Questions about the relative polar curve? Why? What? If when I sketch the next proof and the proof after that, you still have that question, you should ask. Because it should become obvious that it comes up in all the Milnor fiber stuff. But if, seriously, I'm not joking, I hope it will become evident. Why they started considering it, honestly, I probably haven't looked at those exact papers in 20 years, so I don't remember which results they were after at the time. In 73, I'd have to look. But certainly when you're considering a family, which you frequently are, it seems very natural since it's the union of all the critical loci of the members of the family minus the critical points that are actually in the big, that are on the hypersurface itself. Right. All right. What does this have to do with anything? Let me, since I think I can do it in 10 minutes, maybe I will not sketch the proof for an isolated hypersurface singularity and why the Milnor number is what it is, and the Milnor fiber has the homotopy type bouquet of spheres. But let me go with Lay's attaching result, which is from, 78 sounds good. I don't think I wrote down when it is. Did I write down? It's in the notes. I'm going to say circa. Circa 1978. I don't. It's probably maybe earlier. And what does it say? For a generic, so still, F, I just want to get the dimensions straight for you. For a generic linear form, the Milnor fiber, for generic linear form, is obtained from the Milnor fiber of F restricted to where the linear form is 0. So a hyperplane slice of the Milnor fiber is obtained from this by attaching First of all, we're going to apply Morse theory to the norm of a complex function squared on the Milnor fiber of F. The Milnor fiber of F is one dimension less than this. It is n-dimensional, complex n-dimensional. But what I said before is all the non-degenerate critical points of the norm of a complex analytic function squared, all the indices are exactly middle dimension, so n. So this is by attaching a certain number of n cells, and that number is the intersection number n cells. This is an intersection number, which I will explain, if not today, then tomorrow. An intersection number of the relative polar curve with the hypersurface itself, an intersection number. That intersection is proper. It's another one of the exercises in my notes that the relative polar curve intersects V of L properly, so in dimension 0, so in an isolated point, if and only if that's true for V of F. So Lay's result tells you how a bigger Milnor fiber is obtained from the Milnor fiber of a hyperplane slice up to homotopy. Is obtained, first of all, my English is awful, is obtained up to homotopy. Up to homotopy by attaching from there. Okay. This is awesome. Assuming you can calculate these numbers, inductively you can keep slicing, and it will tell you the Euler characteristic of the Milnor fiber. It will put bounds on the Betti numbers of the Milnor fiber. It's very nice. It's very enjoyable. It will give you Kato and Matsumoto's result, that the Milnor fiber is n minus s minus 1 connected, because attaching cells in cells doesn't affect homotopy in 2 lower dimensions. So in dimension n minus 2 and lower. How is this proved? I've got 5.5 minutes. That's easy. Let me assume that I have, this is something I do all the time for ease in writing things. I assume that I have rechosen my coordinates in a generic linear way so that this generic linear form is actually my first coordinate. Right? That's no loss of generality, it's just a gain in easy notation. So you can assume that you've done things so that your first coordinate is this generic linear form. How does this proof go? Well, there's the sketch. the hard part, easily the worst part, is to prove that you can use neighborhoods of the form a small disk cross a ball in defining the Milnor fiber up to homotopy. I am not going to do this. It's very technical. It is not illuminating. But the point is, instead of using an open ball, so this is the Z0 coordinates, and these are all the other coordinates. The point is, you need a polyball, and it's not a disk in the other direction. So you need one of these things to really do this. And you have to prove that that's fine for defining the Milnor fibers up to homotopy. But assuming you've done that, what else is left? Well, you also need to know, there are other things you need to know, like you need to know that you can, for generic choice of Z0, that Z0 restricted to this open, you also need Z0 restricted to this open disk crossed with the boundary of the ball. The closed ball has no critical points. So this is what Mundo was asking about. And when I said, I'm going to need that. I need it now. I'm going to assume this has no critical points. That is actually not difficult to do. I'm just only have 2.5 minutes. So I'm not going to do it. And it's a good exercise to convince yourself that, oh yes, in that slice I can avoid critical points on the boundary of the ball. And then what do? Actually, it's so simple. Let the norm of Z0 squared as a function on the Milnor fiber grow from slightly greater than 0 to tau. I told you that you had a problem where, with the norm squared, where the function is 0. So we really can't start there. All of those all the points where Z0 is 0 are degenerate critical points of this function. But you can start from slightly bigger than there. So you now take another number that's smaller than all the other numbers you picked, so smaller than epsilon, smaller than tau. And Z0, you need to also know that you can do this so that 0 is not a critical value of that there is no critical value of just the function Z0 restricted to the Milnor fiber. Don't take the norm, don't square it. That 0 is not a critical value. But then, yes, in fact, that one can stay open, but then close this one. Because of this and because of this, then for a value slightly smaller than 0, so in a little disk around 0, smaller than that disk and smaller than this disk, as Pepe said in his talk, everything is trivial. Everything's a cross product and looks just like this up to homotopy. It's crossed with a disk. And then you grow from there. You just let this grow. And because you picked it generic, you hit only complex non-degenerate critical points, which means real critical points of that function of middle index, and tomorrow I will count them. If you look at what that says, it's you need all the partial derivatives other than z naught to be 0, which defines that off the hypersurface, and then you intersect with where f equals a small value because you're on the Milnor fiber. That's what this intersection number is. I'll talk about it more. And this plops out, and you get this. I know that was quick, and I skipped every technical detail, but I'm already 1 minute over, so I must stop. Thank you. But I can say that last part more carefully tomorrow. Do the exercises.